Beneath a roof of steel and glass, the world's largest concrete 3D printer moves with patient precision, layer by layer, reimagining what a factory can build.
Tired and the precision of a device that never makes mistakes. The positioning system uses a combination of optical encoders on the drive motors and laser interferometry sensors that verify actual position against commanded position 12,000 times per second. If the system detects a deviation greater than 0.4 millimeters, printing automatically pauses while the error is diagnosed. Watch the first layer go down on a fresh foundation. The concrete flows from the nozzle like thick toothpaste, viscous enough to hold its shape, but fluid enough to self-level slightly, eliminating the tiny air gaps that would weaken the structure. The sound is surprisingly subtle, a soft, continuous hiss from the pump, combined with the low hum of the gantry motors. There's something almost meditative about watching the process once you settle into its rhythm. The nozzle traces the outline of a wall, reaches a corner, executes a precise 90-degree turn, continues to the next corner. Each complete circuit takes between 7 and 12 minutes, depending on the complexity of the geometry. Within 8 minutes of deposition, that first layer has achieved enough structural integrity to support the next. This is where the chemistry becomes almost magical. The accelerants in the mixture create a hydration reaction that generates heat. You can actually feel it if you place your hand near freshly printed concrete. And that heat accelerates the curing of the layer above it, creating a cascading reaction that strengthens the entire structure from the bottom up. By the time the printhead completes its circuit and returns to deposit the next layer, the previous one has reached a compressive strength of approximately 3 megapascals, enough to bear the weight of additional layers without deformation. Not yet strong enough to walk on, but strong enough to build upon. The strength will continue developing for 28 days, eventually reaching a final compressive strength, exceeding 45 megapascals, stronger than most conventional poured concrete. The walls themselves aren't solid blocks of concrete. They're printed with a sophisticated lattice interior. Imagine a honeycomb structure rotated at strategic angles and optimized through computational structural analysis. This isn't just about saving material, though it does reduce concrete usage by nearly 40% compared to traditional solid construction. The lattice pattern serves multiple critical purposes. It creates natural channels for electrical conduit and plumbing lines to be threaded through after printing, eliminating the need to cut holes through finished walls. It provides precisely sized cavities for insulating foam to be injected, creating a thermal envelope that dramatically outperforms conventional insulation approaches. And perhaps most importantly, it actually increases the wall's structural performance by distributing loads across multiple contact points, rather than relying on material bulk alone. A solid concrete wall of equal thickness would actually be weaker under certain load conditions. Every 90 minutes, the machine pauses. This is where the 3 technicians on site earn their keep. They approach the most recent layers with tools that look like they belong in a dental office. Small picks for removing any irregularities, calibrated moisture meters that measure water content to verify proper curing conditions, and laser measurement devices accurate to within half a millimeter that confirm dimensional accuracy against the original digital model. They're also watching for something called delamination, a phenomenon where one layer fails to bond properly with the one beneath it, creating a hidden plane of weakness invisible from the outside. The causes can be subtle: a temporary drop in ambient temperature, a slight pause in material flow, even vibration from nearby equipment. In 7 years of commercial operation, this facility has experienced only 2 delamination events, both caught within minutes by experienced technicians and repaired using a specialized bonding protocol before they could compromise the structure. But here's what makes this process truly fascinating and addresses the most common criticism of 3D printed buildings: the integration of structural reinforcement. Traditional 3D printed structures have faced skepticism because concrete, for all its impressive compressive strength, is notoriously weak in tension. A concrete column can support enormous weight pressing down on it, but will crack readily if bent or twisted. Without steel reinforcement, a printed wall cannot safely resist the lateral loads generated by wind, earthquakes, or even the gradual settling of soil beneath the foundation. Early 3D printed buildings were limited to regions with minimal seismic activity and strict height restrictions because engineers couldn't certify their performance under dynamic loading. The solution developed for this facility is elegant in its simplicity. At pre-programmed intervals determined by structural analysis, the printhead pauses while automated insertion tools mounted on a secondary gantry system place steel rebar sections into channels printed directly into the wall geometry. These channels are designed with specific dimensions, slightly oversized to allow clearance for the rebar, with textured interior surfaces that maximize mechanical bonding with the grout. Once the rebar is positioned, a AHI'd specialized grout mixture, faster curing than the print material and formulated for maximum adhesion, is injected to lock the reinforcement in place. The entire insertion and grouting process adds less than 4 minutes to the print cycle for each reinforcement location. When printing resumes, the next layers encapsulate the grouted rebar, creating a composite structure where steel handles tension and concrete handles compression. The result meets or exceeds every requirement in the international building code for seismic zones up to Category D, the second highest classification suitable for regions like California, Japan, and Turkey. The mansion taking shape on the print platform today includes features that would have been prohibitively expensive or practically impossible using traditional construction methods. The entrance foyer features curved walls that flow organically into the living space, transitioning from a tight radius of 1.8 meters to a gentle arc that opens into a double-height great room. A traditional contractor would have required custom-bent steel framing and hundreds of hours of skilled labor just to create the formwork for these curves. Integrated niches for artwork are extruded directly from the wall structure, eliminating the need for framing and finishing. A spiral staircase rises from the main floor as a continuous helical form, each step printed as an integral part of the central column. The architect who designed this home, a Danish-American, who trained at the Architectural Association in London and now specializes in computational design, told me that his original vision would have required over $2 million in custom formwork alone using conventional construction methods. The complexity would have made the project commercially impossible for any but the wealthiest clients. With this printer, the curves cost exactly the same as straight lines. The spirals cost exactly the same as simple rectangles. The machine simply follows. The coordinates in the file, indifferent to the complexity that those coordinates represent, a straight wall and a curved wall require the same time to print. A 90-degree corner and a flowing organic transition require the same effort from the machine. This economic reality is quietly reshaping architectural possibilities. After 72 hours of continuous printing, interrupted only by the 90-minute inspection intervals and 2 scheduled maintenance checks on the pumping system, the structural shell is complete, but the home is far from finished. What happens next is a hybrid process that combines the speed of additive manufacturing with the craftsmanship of traditional finishing trades. Electricians arrive on site and begin threading wiring through the pre-printed
Layer by
conduit
layer,
channels,
the printer lays out
pulling
a routine with
cables
its own
through
drainage
passages
channels,
that
shaping
were designed
concrete within a
specifically
millimeter
for
of
this
layer.
purpose
Each pass
and
mounts
printed
into the
with
last,
smooth
forming a watertight
interior
pathway, while the
surfaces
spine
that
between them is
prevent
typically
insulation damage. Plumbers install copper and PEX
On the
supply,
left, a conventional
lines
house after
using
2
the
weeks.
integrated
Lumber,
chases
nails,
built
and human
into the
muscle
wall
slowly raising
geometry,
walls.
positioning
On the right, a
drains
3D
at
printed
precisely
home on
the
its second
location
day.
specified in the digital model.
Each sample
A
begins as a
specialized
fluid mix of
insulation crew
cement,
sprays
water, and
closed-cell polyurethane
Penetration
foam
and texture
into the
tests
lattice
confirm
cavities through
consistency at the
injection
microscopic
ports,
level.
printed at
Rotating the
regular
main volume
intervals
here,
along the wall
you can
height.
see how the roof line
The
steps back
foam
to catch the light.
expands to
Because
fill
it's a
every
self-facing
void,
clerestory. These walls are printed
creating an
40 millimeters
insulation
fast.
envelope
Exactly. Layer
that
data is here.
achieves an
Compression
R
being
value of
solid.
38, nearly double the standard for conventional construction in this climate zone and far exceeding the minimum requirements of any energy code in North America. The thermal performance of the finished structure is so efficient that the HVAC system specified for this mansion is less than half the capacity that would be required for a conventionally built home of equivalent size. The exterior receives a weather-resistant elastomeric coating applied by a second robotic system, a smaller mobile unit that navigates around the structure on a tracked platform. This coating bridges the microgaps between printed layers, creating
Layers
a
of printed
waterproof
concrete
envelope
ripple like growth
that
zones, but
flexes
under
with the
focused flame,
slight
they
thermal
blacken, crack, and
expansion
reveal how
and
heat moves through the
contraction
wall.
of the concrete.
Thermocouples embedded
The
between
interior
layers log the
walls
rise and
are
course.
finished
Layer
with a
joints are consistent,
thin
about
skim
4
coat
millimeters. No
of
visible cold joints at the
gypsum-based
window header.
compound,
Compression feels solid,
typically
no flaking
3
or
to
dust.
5
Outlet
millimeters
boxes
thick,
flush, tight to
that
the print line.
transforms
Moisture
the
readings
visible
clean,
layer
documenting for
lines into
each ridge is
smooth,
checked first with
paintable
calipers,
surfaces
defining the layer thickness to a
indistinguishable
hundredth of a
from
millimeter.
conventional
A laser push
drywall.
measures the run of the wall,
Windows and
while the
doors
rotating scanner
slide
maps the
into
whole facade in
openings
3
that were
dimensions.
printed to
Windows are
exact
still up
manufacturer
nice with 4 returns,
specifications,
reading steady at
with
-0.2.
tolerances tight,
Sliding normal,
enough
smooth,
to
live
eliminate the
sketches.
shimming,
White
adjustment
cycle, no
and
issues
trim
logged.
work
And with that,
that traditionally adds
Careful with that
days
box,
to
it
the
has all the
installation
goods.
process.
It's heavier than it
From
looks.
completed structural shell to move-in ready condition, the finishing work takes an additional 3 weeks.
Every drop is
A
engineered,
comparable,
reinforced with
traditionally
recycled
built home of
microfibers
this
and
size
responsive
and
to additives
complexity
tuned at the micron
typically
scale
requires
and printed. The
16
base
to
locks
20
into
weeks
precise
of
layers,
finishing
forming lightweight
after
lattice geometry.
framing is
Layer by
complete.
layer, the
The
concrete printer
time
built
savings
this house less
compound
than a
at
month ago.
every
Today,
stage.
it sits
The
inscribed with
completed
a brick
mansion
bungalow
will
with
sell
frame
for
cottages
approximately
that have lined this street
$2.3
for
million
decades. Listen
in a market where conventional luxury construction starts at $550 per square foot. A comparable home built using traditional methods in this location would cost closer to $3.1 million and take 14 to 18 months to complete. But the buyer isn't just getting a cheaper house. They're getting a structure with thermal performance that will reduce energy costs by an estimated 40% over its lifetime. They're getting walls that are completely immune to termites, wood rot, and the moisture damage that plagues conventional framing. They're getting a construction accuracy that eliminates the settling and cracking that most homeowners accept as inevitable within the first 5 years. And they're getting a home whose concrete structure will remain standing with proper maintenance for centuries, long after wooden frames would have returned to dust. But luxury mansions in developed markets are only the beginning of where this technology matters. The same company operates facilities in 3 countries now: Denmark, Germany, and the United States, with 2 more under construction in Saudi Arabia and India. In these expanded operations, the focus has shifted toward volume production of affordable housing units. A standardized 3-bedroom home design can be printed in 18 hours, finished in 8 days, and sold at price points that undercut conventional construction by 35%, while delivering superior energy performance and durability. A partnership with a European Space Agency announced last year is developing a modified version of this technology designed to print habitats using lunar regolith, the rocky soil covering the moon's surface. The concept eliminates the impossible economics of transporting building materials from Earth by using resources already present at the destination. Prototype tests using simulated regolith have successfully produced structural elements with compressive strength exceeding 20 megapascals. The First demonstration prints on the lunar surface are planned for the early 2030s. Disaster relief organizations are testing mobile versions of printing technology capable of deployment within 48 hours of activation. A containerized system developed for this purpose can begin printing emergency shelters 8 hours after arrival at a crisis zone, producing 4 complete units per day with a crew of just 6 operators. The implications for earthquake response, refugee housing, and post-hurricane reconstruction are profound. And on a dusty testing ground in the Texas desert, just 50 miles from the border with Mexico, engineers are prototyping the machines that may one day print the first permanent human structures on the surface of Mars. The constraints are extraordinary: extreme temperature swings, an atmosphere too thin to support human life, and a 9-month delay for any replacement parts. But the basic principle remains the same. A robotic arm, a specialized mixture and layer upon layer of patient deposition. Every layer of concrete this machine deposits represents something larger than a single home. It represents the possibility that construction itself, an industry that has resisted automation for generations, an industry built on muscle and tradition and resistance to change, might finally be ready to transform. The techniques you've just witnessed are less than a decade old. The structures they create will stand for centuries. And somewhere in a research lab right now, working late under fluorescent lights, an engineer is already designing the printer that will make this one look as primitive as a stone chisel. The future is being built, one layer at a time.